Welcome! These videos were recorded while I taught topics in econometrics over Zoom, but they were edited so that the student faces, their questions, and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you will enjoy them anyway. Bye now. All right, well then, let's get started. Today we have our 8th lecture, and we are going to talk about local asymptotic normality. Okay, and so today is going to be the last lecture in this group, where we're going to conclude talking about the deriving local asymptotic power approximations that we started in the symmetric location model a couple of lectures ago. And then we moved to talk about contiguity and Lecomte's third lemma and so on. And so what we're gonna do today is to just put together the final piece of the puzzle, which comes in this notion of local asymptotic normality and the so-called differentiability in quadratic mean that we're gonna present today as well. So let me put some context between where we were and where we're going. So as I wrote here, so far we talked about absolute continuity and likelihood ratios. We did that last time. We presented the notion of contiguity, and we presented Lecomte's first lemma. We gave us some way of talking about contiguity. In particular, we saw this specific case in which the log likelihood ratio was asymptotically normal, and we know that in order for the distributions to be contiguous, we needed this relationship between the mean and the variance, mainly that negative half of the variance was the mean. And then we talk about Lecomte's third lemma, which look very powerful, and to provide limiting distributions under contiguous alternatives. But when we apply this lemma to the Wilkinson sign rank test in the symmetric location model, we saw that it was difficult to apply without having or knowing the behavior of the log likelihood ratio, so we just assumed normality at that point. Today, we're going to go back to that and say, okay, what if we don't assume normality? What can we do? Well, we're going to have this notion that is called local asymptotic normality. Just going to be a notion that is going to tell us that the log likelihood ratios look like the log likelihood ratios from a normal model. And so, at least, asymptotically. And then we're going to see what this notion actually is. Why is it useful? In particular, it will be because of the connection to Lecomte's third lemma. And then we're going to provide a sufficient condition for local asymptotic normality known as differentiability in quadratic mean, or QMD, or Hellinger differentiability sometimes. Okay, we're going to just call it differentiability in quadratic mean. And then we're going to see how that is a sufficient condition for local asymptotic normality. In the middle of that, we're going to also learn a lemma that is going to give us sufficient conditions for differentiability in quadratic mean that are going to be easy to check. And at the end of the day, those are the conditions that we're going to be using in the applications that we have to limit distributions under contiguous alternatives. Okay, and then we're going to put and apply everything together in the symmetric location model with the t-test, the sign test, and the Wilkinson sign rank test, and then we're going to wrap up there. Okay, good. So we're going to start with the concept of a statistical experiment, which is something that Lecomte introduced, which is equivalent to, say, model. We're going to be using model, but you're going to see a statistical experiment sometimes, especially if you read some of the references that are related to this class. And, let's just read here and then let me make some comments. The observed data is just going to be a sample x1 through xn from a distribution p theta. And p theta is some measurable space, script a, x, and script a. And the distributions are going to be indexed by a parameter theta. The sample, you can view it as a single observation from the product measure p and theta, which in the case of IID data is just going to be n copies of p theta. And the statistical model, also called the statistical experiment, is completely described as a collection of probability measures p, theta, n. So in simple terms, the statistical experiment just has the model given in p theta and the sample size n. Okay. And today we're going to study conditions under which the statistical experiment can be well approximated or approximated by a Gaussian experiment. after some suitable reparametrization. And so if this is the goal, is what we're going to do at the end of the day is give me a model, and I'm going to tell you whether, the model or the experiment, can be approximated by a Gaussian experiment. The starting point should be to understand how does it look, say in particular, the log likelihood ratio of a Gaussian experiment. So we're going to do that next. All right. So this is called a normal location model, because we're going to consider families of distributions p theta that are normal with mean theta and variance sigma square, where sigma square is known. Okay. So in this case, if you compute the log likelihood ratio, where again here we're looking at sequences of distributions that are local to theta naught. So these are theta naught plus h divided by square root n, and these are just the distribution at theta naught. Then you have the usual e to the negative half, blah, blah. And so when you take the logs, you have negative 1/2 sigma square, the sum of x minus the mean. The mean of this distribution is theta naught plus h divided by square root n. And so this is negative theta naught, negative h divided by square root n square. And then you have the term that is related to the second part, which is the distribution with mean theta naught. And so we have the sum of xi minus theta naught square. Okay, both have distribution sigma square, which again we're assuming here is known. Then you rearrange terms, and then you end up with this object over here, 1 over sigma square, the sum of xi minus theta naught h divided by square root n, and then you have this non-random term right here. And if you reaccommodate terms and then you just divide and multiply by square root n, you end up with square root n x bar minus theta naught divided by sigma square times h. And so in the end, we can write this log likelihood ratio in the Gaussian experiment like this, where lambda n is square root n x bar minus theta naught divided by sigma square. Okay, notice that it's not divided by sigma, it is divided by sigma square. And so this has distribution that is normal according under p theta naught with mean 0, because that's the mean under p theta naught, and variance even to the so-called Fisher information we're going to see in a minute. And then this is just 1 over sigma square. And so when you look at that, we see that here we also had 1 over sigma square. And so that's why we wrote here 1/2 h square and the Fisher information. So when you realize that delta n has this distribution, it follows immediately that the log likelihood ratio has a normal distribution with mean negative half h squared divided by sigma square and variance h squared divided by sigma square, which in other words shows that we have this relationship between the mean and the variance that we discussed when we were talking about contiguity. Okay. And so, and again, whenever we make distributional statements like this or like this one, we need to be clear about under what distribution. And here we're making the statements under distribution p theta naught. Okay, so this is how the log likelihood ratio looks in a normal location model. And so we're going to start asking ourselves, if you give me a different model, distributions that are not normal, whether they have a log likelihood ratio that looks like this or not. All right. Then it comes this notion of local asymptotic normality. It says traditional regularity conditions for maximum likelihood theory involves existence of 2 or 3 derivatives of the density function together with domination assumptions to justify differentiation under integrals. Lecomte in the 70s noted that such conditions are unnecessarily stringent, and he showed that the traditional conditions can be replaced by a single assumption of differentiability in quadratic mean, or QMD. Lecomte showed that QMD implies a quadratic approximation property for the log likelihoods known as local asymptotic normality. So what is that? Well, here's the definition. The statistical experiment is called local asymptotically normal at theta naught if there exists a sequence of stochastic vectors, delta n theta naught, and a non-singular k times k matrix I theta naught, such that delta theta naught conversion distribution to a normal with mean 0 and variance I theta naught under p theta, and such that the log likelihood ratio of this model has this representation where the first part is exactly what the log likelihood ratio of a normal location model looks like, and the second part is a reminder that goes to 0 as n goes to infinity. So you see here that this is sort of like in the vector case. So instead of having h squared here, we have a quadratic form with the Fisher information. But other than that, we have h times the variable that is asymptotically normal. We have that here. And then we have a non-stochastic term that is a half times h squared and the Fisher information. So when we say that then a model is local asymptotically normal, what we mean is that the log likelihood ratios, okay, are take essentially the form of those in a Gaussian model plus a reminder. Okay. So let me go over these so-called traditional arguments, okay, so that we understand more or less where this is coming from. Suppose that x is IID from a density little p theta, which is with respect to some dominating measure d mu. And then let's assume that this density is twice differentiable. Then we're going to denote by L the log of the density. And then the derivatives are going to be L dot and L dot dot. First and second derivative with respect to theta at a given x. X here is going to be a fixed point. Later, we're going to evaluate at the sample. Then do a Taylor expansion at x. And this is going to be the log of the density p theta plus h divided by square root n. You're going to do a Taylor expansion around theta. So what is that? That's the log of the density at theta plus h divided by square root n first derivative. This is the difference between theta plus h divided by square root n minus theta. So the difference between these 2 points, well, that's this. Then you have the difference between these 2 points square, and that is h squared divided by n times a half. So the 2 here, and the second derivative. And then you have a reminder that depends on the point x that we're doing, where we're doing this expansion, and is smaller than h squared divided by n, which is the order of this term over here. Okay. So then we're going to sum over the n observations that we have. So now here is xi, and then what we obtain, it's something like this, and we're going to assume for now that this is a small reminder. Here we sum n of these reminders, and you were saying like, well, summing n of these reminders still gives us something that is small. By no means I'm attempting to do this formally. What I want you to show you is essentially how, again, what I'm calling here the traditional arguments work. What are the assumptions that you need behind that so far involve, essentially having these two derivatives and making sure that the reminder over here is small. But then if we just look then at this object, then we realize that over here we have something that looks like the delta n object that we had before. And then over here we have something that is essentially the Fisher information plus little o p1, okay, if you invoke some form of law of large numbers. So you see that this is a term that looks like a term that, requires a CLT type of argument. You have 1 over square root n, the sum of an object that is mean 0. The expected value of the score, which is the first derivative, is 0. And then we have a term here that is an average of second derivatives with a negative sign here. And the negative expected value of the second derivative, which equals the expected value of the score square, is what we call the Fisher information. So when you put these pieces together, you realize by using these Taylor approximations, okay, as long as you have densities that are sufficiently smooth, then you can claim that the models that you're dealing with are local asymptotically normal by virtue of Taylor expansion, okay? And we see here how the log likelihood ratio emits essentially this representation where it has a part that looks like the one in the normal model and a reminder term. Okay? Questions? Excellent. So hopefully that's clear. We can keep going. Now, we have the following observation. Lecomte said, well, in order to get local asymptotic normality, you don't need to assume this like 2 or 3 derivatives that you're going to need to get the first 2 terms and control the remainder. You just need a single condition that involves a first derivative. And that condition is known as differentiability in quadratic mean. Definition goes as follows. A model P is called differentiable in quadratic mean or Hellinger differentiable if theta, if there exists a vector of measurable functions theta, such that as h goes to 0, we have this condition over here. The integral of this bracket square goes to 0 faster than h square. And then the term within bracket involves the differences of the square root of the densities at theta plus h and theta. And then this term over here is 1/2 h, and here's where these functions eta that we have in our definition kick in. So what the definition says is that the family is differentiable in quadratic mean if there are functions etas, where such that this condition over here holds. And so usually this term over here, let me just mark because it's a term that is kind of like the tricky term. Usually that term, at least here in the scalar case, so there's no h prime, h is the scalar here, is the derivative of the map, square root p theta plus h at h equal to 0. Okay? So if you just consider the derivative of the square root of the density, this 1/2 square root of the density times the derivative of the density. Soon I'm going to be calling this to be consistent with the notation that we had before, p dot theta. And then you realize that this is actually the derivative of the log of the density, because the derivative of the log of p theta with respect to theta is just 1/p theta times p dot of theta. Okay, so here you just look at this expression and multiply and divide by square root p, and then you get this thing on the side. So the function eta in the statement of differentiability in quadratic mean typically is given by L dot. Okay, doesn't have to be like that, but this is what we're going to be doing today. And so let's make sure that we recall this connection, that function zeta is just going to be the score, and the score is just the derivative of the log density. So this is the one notion of differentiability that Lecomte uses to obtain local asymptotic normality. And so we're going to see later, as I said, that, functions that are differentiable or densities that are differentiable immediately are going to be QMD, but there are some functions that will not, or some distributions that will not satisfy this property. So this is not a universal property by any means. And whenever you want to prove or want to bring a counterexample to some of these issues, I always say that a useful distribution to prove counterexamples is the uniform. And this is no exception. Here, the uniform provides an example of a distribution that is not differentiable in quadratic mean. So quadratic mean differentiability requires this condition over here. When you compute this difference, okay, it has to go to 0 at a rate that is faster than h squared. Well, in the case of the uniform, notice that we have here p theta is uniform on 0 theta, and p theta plus h is uniform of 0 theta plus h. So let's call this over here star, and then look at S star at the points where the density p theta is 0. What you obtain is the integral where this density here is 0. And then you have square root p theta plus h minus 0 minus 1/2 h eta dot 0 squared d mu. And this is just the integral over p theta 0 of p theta plus h d mu. And this is just the integral from theta to theta plus h of 1 over theta plus h dx, say. And this is just going to be h divided by theta plus h. As you can see, this is linear in h, and it doesn't go to 0 faster than h squared. So you conclude that the family of uniform distributions is not differentiable in quadratic mean. Okay, fine. But then Lecomte said QMD is what you need to get local asymptotic normality. That's the content of this theorem that I'm not going to prove, but you can find proofs in the book by van der Bar and the book by Lemma and Romano. So the theorem says the following. Suppose that capital theta is an open subset of Rk and that the model P is differentiable in quadratic mean at theta. Then 1, the expected value of the score is 0. 2, the Fisher information I theta exists. And 3, the log likelihood ratio takes this form, and that is local asymptotic normality. So this is great because, local asymptotic normality now can be obtained under weaker conditions that assuming, a lot of derivatives and smoothness. We just need to assume one condition, which is QMD. But the problem is that QMD looks like a hard condition to check in practice, okay? And the question then is whether there are simple sufficient conditions for QMD to hold. The answer is going to be yes, okay? And usually, as I wrote here, one proceeds by showing differentiability of the map that is the square root of the density, plus some, integrability conditions that gives us a conversion theorem for integrals, okay? And those are the two things that we want. And so essentially everything here is summarized in the next lemma, which I am going to prove just because I think it illustrates how you can really get differentiability in quadratic mean by assuming continuously differentiability. Okay? So the lemma reads as follows. For every theta in an open subset of Rk, let p theta be a mu probability density. Assume that the map theta to s theta, which is defined here as the square root of the density, is continuously differentiable for every x. We're going to assume that the elements of the matrix I theta, which is what we're calling the Fisher information, here defined as the integral of p dot divided by p dot divided by p prime p d mu, are well defined and continuous in theta. Then this map is differentiable in quadratic mean with eta given by this ratio over here. Remember that differentiability in quadratic mean has eta in its definition, and we're seeing here this eta is just this object that appears here in the definition of Fisher information. So we're going to prove this in 2 steps. And the first step, we're going to argue that p theta exists, and we're going to find expressions for S dot. And in the second step, we're going to invoke VITALI'S theorem, which I'm going to state what it is, but it's essentially the theorem that is going to give us conversions of integrals. And we're going to show that that immediately gives us differentiability in quadratic mean. A word of caution here is that, well, not a word of caution, it's sort of like a comment, I'll say. There are different versions of this lemma, if you just, depending on the book that you look at. And some you'll say you can actually prove this using absolute continuity here instead of like continuous differentiability. Some will like give you that this mapping here is well defined as part of the result. I'm just going to use this version because it's the one that is simplest to prove, and at the end of the day conveys sort of like the intuition that I want you to keep in mind. Okay, but if you just, there's something that you care about and you start looking at different references, you're going to find versions of this that are slightly different to each other. And I personally don't know which is the original one or anything, so don't ask me that. Okay, so you guys ready? Let's go. Okay, step 1, we're going to argue that p theta exists and find an expression for S theta naught, S dot theta, sorry. So let's say the following. Let the map S theta square, okay, which is P theta, is continuously differentiable by the chain rule. Then, whoops, then I'm going to say, note that P theta dot equals 2 S theta times S theta naught. Okay, so here we have an expression for P dot. I'm going to say, note that S dot theta must be 0 when S is 0. And then to see this, know that if you just plot this function as a function of theta, and this is a continuous function, and then if it touches 0, since S theta is non-negative, it must be that if S theta is 0, the derivative has to be 0, which is what we're saying here. And so the same thing happens then for P dot theta has to be 0 when P theta is equal to 0. And so, eta theta, which is the ratio here of P dot divided by P, we can define as 0, or actually anything else, but we're going to define it as 0 when P theta is equal to 0. Okay, so P dot exists as well defined. So we need to find now S dot, and then S dot theta is just the derivative with respect to theta of the square root of P theta. And this is related to something we did earlier. So that is 1 over 2 square root P theta times P dot theta. Now let me multiply and divide by square root of P theta. And this is what we obtain. So we can actually write this as 1/2 eta theta times square root P theta. And actually, for something I'm doing later, I can write as 2 S dot theta being equal to, or actually, this implies, because this is exactly what I'm going to use later, 4 S dot square equals eta square P theta. And why is this useful? Because before we said, okay, the Fisher information, I theta, was the integral of actually eta square P theta d mu. And so we're saying that the Fisher information we can write as 4 times S dot theta square d mu. And this is finite and continuous in theta. Okay? So that's that. That's the first part of the proof. Second part of the proof, as I said, involves arguing that certain integrals converge. So let's do that. To do that, we're gonna invoke this theorem known as VITALI'S theorem, and it says the following: it says you have two conditions. If the first condition you have a sequence of functions that converge to f mu for mu almost every x, okay, and you have that the lim sup of the square, the integral of the square of the sequence is bounded by the integral of the square of the limiting function, which is also assumed to be finite. Then you have that the limit of the square difference of these two objects, okay, with respect to the mu is 0. And it's going to turn out that this last part, this conclusion, is exactly the definition of differentiability in quadratic mean. So all we need to do to argue that we get to the end is to show 1 and 2, okay, in the context that we're studying. So first, theta, the mapping theta to S theta is continuously differentiable, okay? So if we define f of h as 1 over h, and then s of theta plus h minus s of theta, and this is a function of h, it's not a function of n, but this is just notation, right? So these statements are as n goes to infinity, and here we're going to have statements as h goes to 0. So imagine that h is just 1 over n if you want to make it, connected somehow. And then by continuous differentiability, we know that this is the definition of the derivative, okay? So f of h converges to f, which is the derivative of s, okay, as h goes to 0. So the first part of VITALI'S theorem, which is this over here, follows by our assumption that this function s is continuously differentiable, okay? So that's that. So we're good then. The part that we need to prove is this second part. And the second part involves this inequality over here that I want to do next, okay? Questions? Okay. So let's do this. All right, let me take this. So this is what we want to prove. This inequality, which is the second condition in VITALI'S theorem. And we're going to do this by using f of h defined like this and f defined like this, which are the two objects that we showed that converge pointwise, okay? So then notice the following. 1 over h, 1 over h times s of theta plus h minus s of theta. I'm removing the dependence on x because it doesn't help much here. So it's 1 over h, the integral from theta to theta plus h of s dot b db. And let me now introduce a change of variables, defining b as theta plus uh, so that db is equal to du, and then u here is essentially taking values between 0 and 1. So then this over here is just h divided by h, because this is wrong, sorry. db equals h du. So this is integral from 0 to 1 of s dot, and then b here is theta plus du. Okay, nice. So then next, notice that when you grab this object and take the square, just going to be the integral. Notice that these h's here, of course, cancel out. So it's going to be the integral of s dot theta plus du square. This is less than or equal than the integral from 0 to 1 s dot square theta plus du by here I'm using Jensen's inequality. And so this is key because notice that what we're trying to check here, this condition, is that the integral of this fh function square, which is this object over here. And so essentially what we have here is fh square is less than or equal than the integral from 0 to 1 of s dot square theta plus uh du. Okay? Are you guys following? Questions? We're good. Okay, so we can keep going. We're getting to the end. So now let me just take the integral then. I'm going to be using this inequality over here. So we're going to be saying, okay, the integral of f square h d mu is less than or equal than the integral of the integral from 0 to 1 s dot square theta plus du d mu. And then what I want to do now is to change the order of integration, which you can do by invoking, say, Fubini's theorem. It's the integral of s dot square theta plus d mu du. Oh, I don't have space to do the... Okay, let's just write it again. So this is the integral from 0 to 1. And let me write 1/4 here. Integral 4s theta plus d mu du. And notice, this integral over here is the Fisher information at theta plus This is what we derive in the first step. Remember that we wrote the Fisher information as the integral 4 times this function s dot square. Well, that's exactly what we have here. And so this converges as h goes to 0 to 1/4 the Fisher information at theta. Okay, because I theta is continuous at theta. All right, so then you put things together and you have that the limit as h goes to 0 of the integral of s f h squared d mu is less than or equal than 1/4 the Fisher information at theta. Okay, but this is just the integral of s dot square theta d mu, which is the integral of f d mu square, given our notation for f and s dot. And so this is the second condition in VITALI'S theorem, and we can invoke VITALI'S theorem to reach the conclusion of the proof, which says if you apply VITALI'S theorem with this choice of f of h and this choice of f, you have this result. The limit of the difference of these two square is 0, okay? And then if you just notice that s theta is square root of that, and then we also show that s dot theta was this, and then you plug in all these things, okay? And you take, the 1 over h that appears to the other side if you want, or whatever. You're going to notice that this is exactly the definition of QMD. And that's that. So notice how we prove the one condition that we need for local asymptotic normality, which is differentiability in quadratic mean. We prove that condition um, by simply using the density was continuously differentiable. Okay. And so, as I said, it's not that I particularly care. I mean, the lemma is really useful, but it also gives you an idea on how you actually can get this by simply using some form of like pointwise convergence that is given by the continuous differentiability, and that the same object is giving you this convergence theorem for integrals. Okay. And so you put the pieces together and you get QMD, which in turn gives you local asymptotic normality, which in turn allows us to use Lecom's third lemma. Okay. Questions about this before I continue? Okay, so let's continue. Example is going to be the location model, the symmetric location model we've been using before. And so let P theta be the density that is given by F, which is the density in the symmetric location model, where F is continuously differentiable. Okay, we're going to let L dot here, the score, be P dot divided by P, which in this case just like F prime F. And here I'm sort of like mixing notation because I'm denoting the derivative here by prime and here by a dot, but you get it, hopefully. And so we're going to define it like this whenever the denominator here is positive and the derivative exists, and otherwise zero otherwise. Okay, and we're going to assume that this Fisher information at theta equal to 0 is finite. And so I wrote, since in this model the Fisher information is equal to I theta for all theta because it's a location model, okay, then and so it is continuous in theta, it follows that the family is differentiable in quadratic mean by the previous lemma, because we have continuity of this as a function of theta. This is finite and well defined, and then we have the density that is continuously differentiable. So now we know that the symmetric location model depends is QMD and has score L at theta equal to 0 equal to the ratio of F prime divided by F, which is what we're going to use in the next derivations. Questions? Sounds good. Now we move to the last part, which is limiting distributions under contiguous alternatives. Local asymptotic normality is a convenient tool to study the behavior of test statistics under contiguous alternatives. Local asymptotic normality gives us that, two distributions that are mutually contiguous, okay, have a log likelihood ratio that takes this form, okay? That's what we know. If we mix local asymptotic normality with Lecom's third lemma, then we have the joint behavior of the test statistic and the log likelihood ratios, and that gives us the distribution of the test statistics under the local sequence of parameters, or if you want, the contiguous distributions that are contiguous to the one that we care about. And so the general scheme is typically going to involve two parts. In the first part over here, we're going to consider sequences of test statistics that we can write as in the following form, which is 1 over square root n, 1 over square root n, the sum of a function here that is mean 0, that is known as the influence function. So I'm going to use this letter psi to denote the influence function of the test statistic. And, there may or may not be a reminder term over here, okay? And then we're going to also use that local asymptotic normality gives us that the log likelihood ratios are going to be determined by this expression over here. And the only part that is random here is, again, H prime L dot. So at the end of the day, all the action is going to be driven by the score of the model and the influence function of the test that you are considering. And that's going to be the game. So we put two things together. Here we have the test statistic with an influence function. Here we have the log likelihood ratio with the score. And we're going to look at the joint behavior of 1 over square root n, the sum of these two pieces. Okay? They're going to be asymptotically normal. okay? And the asymptotic normality is just going to be given by this vector that says, the statistic is mean 0, and the log likelihood ratio has a mean that is negative half of the variance. The test statistic has a variance in the limit or variance covariance matrix if this is a vector that is given by the expected value of the square of the score. And they have an asymptotic correlation given by the expectation of the score times the influence function. And this is what we call in Lecomte's third lemma, tau. Tau is going to be important because it gives us the behavior, and in particular the mean or the deviation from the mean under the null of the test statistics under the alternative hypothesis. That's the content of Lecomte's third lemma. So all we need to do when we want to study the behavior of a test statistic like this one, okay, instead of under a distribution p theta, we want the behavior under distribution p theta plus h divided by square root n, is to find out this tau. Once we have that tau, we're just good to go, and we can apply Lecomte's third lemma, and it's giving us everything we want. Okay? Okay. So we're going to apply this to the symmetric location model. And then remember, here p theta is the distribution with density f, that it was symmetric on the real line, symmetric about theta, okay? And this is exactly the same setting we used like 2 lectures ago. The data is going to be IID. We're distributed from p theta, and we wish to test the null hypothesis that theta is equal to 0. So our null distribution is going to be the distribution with theta equals to 0. The new assumption that we're going to impose is that this family of distribution is differentiable in quadratic mean, okay? Which essentially says that this f here is, a continuously differentiable. Here I wrote absolutely continuous because, again, depending on what version you use, but let's stick to continuously differentiable, okay? And it has finite Fisher information at the null given by I0, which is the integral of the score at 0 square times with respect to the density, okay? And remember, this is the score, which at 0 is just f prime divided by f. So by the Land theorem, we know that this is the log likelihood ratio, okay, of deviations, local sequences with respect to the null. So in this case, for us, this is the null hypothesis. These are sequence of local alternatives. So this theta n that appears over here is going to be h divided by square root n. And then we know how this is L dot at 0 of xi. And what we're going to do now is just go over the t-test, the sign test, and the Wilcoxon sign rank test. And then we're going to derive the power under the local alternatives in essentially 1 or 2 lines just by using Lecomte's third lemma and our knowledge on how this model is differentiable in quadratic mean. Okay? Let's start with the t-test. It's always the easiest. Notice, the t-test here, we have square root n x bar n divided by sigma hat n. This is, you can write as 1 over square root n, the sum from 1 to n, xi divided by sigma hat n, right? And then we can just do the usual manipulations here to replace sigma hat with sigma and obtain a remainder term. And so we see then that this is the influence function of the t-test. So what we need is to find tau, right? Tau is the expected value under the null of the influence function, x divided by sigma, times minus h times the score. So let me take out h and sigma outside. Let me write these expectations as an integral. And this is x f prime divided by f times f dx. Of course, these two cancel out. And so this is negative h sigma integral x f prime of x dx. And this is just h divided by sigma. Okay, here I'm going to say integrating by parts. So that's what it is. And so then the limit as n goes to infinity of the power of the t-test along the sequence of local alternatives is 1 minus the CDF of a normal at the quantile minus tau, a result that follows immediately from Lecomte's third lemma. And so this is 1 minus the CDF of the quantile minus h divided by sigma. And that's it. We obtain the local power of the t-test by using Lecomte's third lemma without doing anything, without explicitly making any statement about the behavior of the t-test under the alternative. We just get that from Lecomte's third lemma, okay? But we didn't do any change of variables or anything like the stuff that we did for the t-test before. But arguably, the t-test was easy when we did it a couple of lectures ago. So let's see if what happens with the sign test, which took us a lot more work, and it required us to use CLTs for triangular arrays, and we had to be careful about how to deal with that, and we had to check the conditions of the Lindbergh-Feller CLT to get the behavior under the local alternatives. Well, now we're just going to look at that, and we're not going to need to do anything like that. So let's do that. So here we have the sign test. Remember, the sign test statistic was 1 over square root n, the sum from 1 to n of the indicator that xi is positive minus a half. So here, this is just the influence function. So tau here is expected value under the null of the indicator xi positive minus a half times minus h f prime divided by f. So tau is, let me say, negative h. And the half here disappears because expected value of the score is 0. So I can just deal with the first term. And this is going to be the integral from 0 to infinity of f prime of x dx. And then this is just h at f0. And so the limit as n goes to infinity of the power of the sign test along the sequence of local alternatives theta naught is 1 minus the CDF of a normal at the quantile minus tau. And this is 1 minus the CDF standard normal at z1 minus alpha minus h f of 0. And you see how this, well, first is exactly what we obtained a couple of lectures ago. And then also it shows what I said before, that we could derive the behavior of the test under a sequence of local alternatives without any usage of CLTs and so on that require triangular arrays or anything like that. It's just an immediate consequence of Lecomte's third lemma. Okay, good. Finally, we have the Wilcoxon sign rank test. So remember that we denote this test statistic. Um, we call it like what? W. Wn equals n minus 3 half sum from 1 to n of the ranks times the sign of xi. And then we show that day that you can write as 1 over square root n the sum of these random variables that are called ui at the time. The ui's were just g of the absolute value of xi, where g was the CDF of the absolute value of x times the sine of x plus little op1. And so here again, this guy is the influence function. And so if we want to compute tau, is the expected value under the null of the influence function, g absolute value of xi times the sine of xi times negative h and the score f prime divided by f. Let me take h out. And I'm going to use that g of the absolute value of x is just 2 times f minus 1. And so the sign is 1 if x is positive. So this is going to be the integral from 0 to infinity of 2 f xi, well, x, let's call it x, minus 1 times f prime x dx minus the integral from negative infinity 0 of the same object and then again, if you integrate this by parts, you get that this is 2h times the integral of f squared dx. I'm saying here integrating by parts. So, again, putting things together, the limit as n goes to infinity of the power of the Wilcoxon sign rank test along the sequence of local alternatives is 1 minus the CDF of normal minus tau. Here I'm just going to write it 2h integral f2 squared dx. Done. Notice how convenient this was because the behavior of this test statistic under the local alternatives is convoluted at the very least. And notice that in the previous class, we did this in the context of the normal location model. We didn't have this. We had something that looked like, square root pi divided by something. And so, well, that's because in the context of the normal model, that's exactly what this integral equals to. Okay, but then that's what we get. And then hopefully this gave you an idea of how you can apply these tools that we developed in the last few lectures, mainly contiguity, Lecom's third lemma, and local asymptotic normality, into the context of this example that we call the symmetric location model, and how you can use these tools to derive local asymptotic power. So sometimes, it will be easier depending on the setting that you're considering to just derive local asymptotic power curves by using, let's say, the traditional approach. And they're just going to derive distributions under the null, under the alternative, and then, put things together. And in other contexts, perhaps investing in tools like this is going to be, it's going to have a higher payoff, okay, depending on what you're doing. If you're not the type of person that is doing econometric theory, but you're more like a user, An important thing to notice, I'll say two. One, you get exposed to, you get exposed tomorrow to a paper, and then that paper is, you know, using contiguity and asymptotic normality and differentiability and quadratic mean. And then you know what these things are about. You don't get scared and say like, oh, what is this? You just know what these are about. You have an idea of why they're maybe using these tools. And second, when you hear somebody says like, I'm going to assume but that my model is differentiable in quadratic mean, you don't react with sort of like a skeptic view. People, when people hear like terms that they are not familiar with, immediately the tendency to believe that there's like strong assumptions or anything, when in reality, differentiability in quadratic mean is, as we show, is milder than assuming that the densities have 3 or 4 bounded derivatives that are continuous and smooth and so on. But people are used to that. So if you say like, oh, I have a function that it has 3 bounded derivatives, people say like, oh, fine, I'm gonna assume that this function is differential in quadratic mean. Like, whoa, whoa, whoa. So that's why, for you to avoid to have those type of reactions, it's useful to understand what these concepts are, even if you're not a user of this context. If you're just an observant. So hopefully today's lecture help you with getting some clarity in what's the scope and the implications of these notions. Okay, I think that's about it for today. We're a couple of minutes earlier, but I'm gonna stick here to answer any remaining questions. Okay.